Okay, hello everyone. Once again, today's webinar is going to be related to the SPATRA project, one of the work streams in SPATRA project. SPATRA project is a European research project that aims to improve transport planning and management through the use of satellite-based technologies. It combines Earth observation data with in situ and ground-based data to develop two work streams. One is for the road transport and the second one is for the rail transport. This webinar is going to be related to the rail work stream, which addresses the impact of extreme temperatures on railway infrastructure. We will have two presenters today. The first one is Alina Klapper from OHB, and the second one is Milan Banić from Uni. So Alina, please share your screen and start with your presentation.
Yes, thank you. I will share my screen. So now you can see my screen, hopefully, and
yes, we can see the screen.
Start the presentation mode. So, okay. Also, hello from my side. As introduced, I'm Alina Klapper. I'm working at OHB as a software developer at the Earth observation field, and works here in the SPATRA project for the rail work stream. And I can skip the first slides. It's an overview here for the road and rail use case, as nicely introduced by Alina. Thank you. And my topic would be here for the rail use case, using satellite-based Earth observation data and machine learning to predict rail track temperatures. And I firstly want to start with some motivation of their use case, why we focus on it. And after that, I will go more into details of what we are doing. And also Milan will tell here more details and jump over into the presentation. So everybody knows we have climate challenges. So while the number of hot days is rising, like for example in Germany, also in other cities, you can see here in the left diagram, the number of icy days, so of cold days, is falling, as you can see here as an example on the right side. And these extreme temperatures has also an impact of the rail track temperatures. So the rail track or the rail temperatures can significantly exceed the air temperature, and especially in high temperatures ranges, it differs is over 20 degrees. Can occur. As you can see also in the diagram on the right side, we have here on the green ones the air temperature, and the rail temperature is in red, so significantly higher. And temperatures above approximately 60 degrees are classified as critical. And what could be a possible consequence here is that the track has lateral displacement, so as also called as buckling when it's used from related to heat. As an example, we have during a week in 2017, when air temperatures reached out around 30 degrees, 31 rail tracks deformations occurred in Serbia. And these extreme temperatures can cause a variety of safety risks and also cost on rail transport. We have as a safety risk, for example, danger of derailments, failure of signaling and control technology, increased risk of fire, and health risk of employees or passengers. On the cost side, we have, for example, delays and cancellation, also high maintenance and repairs, and of course also energy cost. Also here some numbers. In 2015, during the hottest day, a July day on record in the UK, there were 12,080 heat-related delay minutes, and an additional 23,700 minutes caused by unplanned train restriction. So what is currently, the status quo. Here currently the temperature mostly benign via the weather forecast of the weather reports or sensors. And they have some disadvantages, but also some advantages. For the weather forecast side, we have, is it cost effective? Is it's also scalable and also predictive. We have it forecasted, but it's often imprecise and also delayed in time. And we have not so local information about the heat. Here came the in situ sensors. They are more precise and also have real-time information and have very local information. But of course, they are not scalable. You cannot put everywhere sensors. And then we have, of course, maintenance is really high. So now the solution would be the satellite-based rail temperature monitoring, which combines the advantage of both of the conventional methods. And as we call it here, the SPATRA rail temperature estimation. Here it would be cost-effective, scalable, predictive, precise. We get real-time information and also can be localized. So what is the concept here for rail buckling or for the SPATRA project? We have the three puzzles, we would say. Here you can see we have the first one, the real-time temperature, as we get from high-resolution land surface temperature in the rail environment. The next puzzle would be here the temperature forecast. So we get rail track temperature prediction also for the 24-hour forecast window. And the last point would get also a buckling prediction for the rail lateral displacement. Okay, I will go here more into details. I will start with the first and jump over to the with the first and go more details for that. Here would be, we call this the thermal downscaling, because we get often coarse satellite data from, or can use coarse satellite data, but we want to get more local information, and here we need some kind of, we call it the thermal downscaling. So the goal would be here to obtain hourly high-resolution temperature data using thermal satellites. For that, we want to use land surface temperature from several satellites. What is land surface temperature? Maybe some of you are not familiar with this. This is everything what the satellite can see from its point of view. So it could be the ground, of course, but it could be also canopy of the trees. This could be the roof of buildings. It could be everything what really satellite could see from its point of view. And this temperature data we will get from 3 satellite missions from the Sentinel-3, which came with a spatial resolution we call 1 kilometer by 1 kilometer, and with a temporal resolution of twice per day. Also similar the Aquaterra Modus constellations, also with the same spatial resolution and also temporal resolution, but it came at different time steps at the day. So we have here, in addition to the first one, but also we want to use called Copernicus Land Monitoring Service LST data, which is a combination of several missions, but it has a coarser spatial resolution of 5 kilometers. But it came really higher in the temporal resolution. It comes hourly. And we want to downscale these 3 satellite LST data in combination with optical data from another mission, from Sentinel-2, which has a more information about the land surface or land characteristics about the area. We calculate some indices about this. As example, the normalized vegetation index that could give us some information how the vegetation is around the area, or also about the moisture, about the humidity, or also an indicator would be building density. Everything that could be calculated from the optical data. And how we want to use that, we want to use a stepwise random forest algorithm to improve exactly the spatial resolution of 1 or 5 kilometers to 500 meters or finer. And this we want to validate against higher resolution LST data from other satellites mission, like Landsat 8 and 9. They came already in higher resolution as 30 meter, but they have a really bad temporal resolution as it comes only by 8 per week, 8 days, every 8 days we get some image. Okay, for that I want to show you more examples. So here's we'll jump over to show some results. On the left side, you can see here an image of the area of on the test track area of Niš in Serbia. You can see the city, Also some forests, some hilly areas, some characteristics on the left side. And it's, as everybody knows, an optical image, like maybe some ever saw in Google or something like this before. And now on the right side, you can see a land surface temperature. So here's really a thermal images. As I called, it's everything the satellite could see from its view. And here one pixel has the dimension 1 kilometer by 1 kilometer. So you get for that area the temperature data. But that's really coarse, so we want to downscale it. On the side, what we are using, what is this stepwise random forest algorithm? For that, I have here the images. So a random forest algorithm is, maybe one of you, all of you knows, is an example learning method that builds multiple decision trees during training and averaging the predictions of the individual trees to produce a mean prediction for regression. But why I called it stepwise? Because in each step of we retrain the model progressively at different resolution levels. So maybe we go and let us see this in the example. Firstly, we start here in the left upper corner. We have the Sentinel-3 LST data of 1 kilometer or 1,000 meters, and get a simple reprojection to the first step. So it's a method that we easily can use, but it can do it not at a bigger scale. But here at 900 meters, we train our random forest algorithm with all the data we have and predict from here to 450 meters. And again, on 450 meters, we retrain our model and predict to 150 meters. And the last step would be here to train again to predict from 150 meters to 30 meters. And here on the right side, I give you an example of this high resolution LST data we already get from Landsat. So we can compare how it looked like. For that, I'll also give you another example. We have here the Sentinel-3 LST data at June and the 19th of June from 2023 in the morning at 8:30 around. And on the left side, you can see the original data it comes from the satellite. In the middle, you can see downscale to 450 meters, the same image. And on the right side, you can see, I don't move the pin right. Okay, again, on the left side, you can see the original one as comes from the satellite. In the middle, you can see the course downscale to 450 meters. And on the right side now, you can see the validation. It's here Landsat, also at the same date, but a little bit later in the day, it's in the morning, it's around 9:15. And when you compare it, you can see really the characteristics as we see on the validation with the course downscaled as an optical view. We also have some, I created some other statistics to see the quality of the result. Here on the left side, we have the difference raster, so of the downscale LST from our side and the validation LST upscale to 450 meters. So, and you can see most of the pixels are here in this blurred gray color. So it is in a difference between 2 degrees plus minus. And on the right side, you also can have, I brought your scatter plot from the pixel correlation for the validation, also the Landsat, already high resolution data to the course downscaled as before. And we see exactly that we want to see. So the pixels are around these red lines, these trend lines. It has a shape of the line. And it's not a cloud or a bulk around it, but we didn't want to see that wouldn't be correlated anyways. So, and these thermal downscaling data, so this high resolution LST data, we now want to use to predict the rail track temperatures already. So the goal would be here to get hourly rail track temperature predictions with the 24-hour forecast windows with the main input of the downscaled LST data. But we also want to combine this with other data, exactly with weather forecast data, especially for 2-meter air temperature and humidity. but it could also be possible to add others like precipitation or wind direction or also wind speed, if necessary or see it's useful. But the most efficient or the most reasonable looks like the 2-meter air temperature and humidity. And also we will combine this with solar effects. So solar irradiance azimuth and altitude. So if we get the intense of the sun and also the angle. And for training, we use also in situ rail track temperature data. So what we get from the sensors that Milan will talk you or will tell us a little bit more in the second presentation. And this data we want to use for, or we train with an extreme gradient boosting model to exactly get this hourly rail track temperature prediction. We validate this data using the internal in situ data we have. Of course, we will make a train and test data split. And also we get several thermal images from the drone measurements to have a validation at a larger scale, not only pointed validation. And at the end of my presentation, I bring to here I have a service mockup from our rail track temperature prediction. You can see here rail tracks overlaid with temperature prediction based on the satellite data, especially with a resolution of 30 meters. It's also the same data as before. And you can see here the railway section around Nice is in the upper right corner above the city. And you can see here the temperatures on the lines, but also when you put markers on some points, you can get the predictions or local information about these temperatures here and get some forecasts for the predictions also for the 24 hours forecast window. Yes, that was for my side. Milan, I think now you are.
Thanks a lot for your presentation. So we will have time for discussion and questions after Milan's presentation. Now Milan is sharing his screen and we can see the screen.
Hi to everybody. My name is Milan Banić. Do you see screen in full screen, please?
Yes.
Okay, my name is Milan Banić and I'm from Faculty of Mechanical Engineering, University of Niš. And I will build up on the results Alina already presented to you. Okay, as we know from the theory, but also from the practice, all the methods for rail track buckling prediction or risk estimation rely on temperature. So we have a classical approach in which every rail segment is divided into smaller segments, which are then subjected to the analysis. Risk buckling value or risk factor is calculated then for each segment based on traffic as well as environmental conditions which are present currently in that segment. The very important parameter is rail network neutral temperature, which is an actual temperature of installation or where there is no force in the rail. If the temperature increases, we know that rail as a steel made from steel will expand, and if the temperature decreases below the neutral temperature, the rail tracks will contract, as there are continuously welded that transmit through the whole track area, and then if the supporting structure is not doesn't have sufficient stiffness, we will have a lateral buckling of the rail. But the problem, as sorry, Alina already said, is that the most rail tracks now in Europe and also worldwide were designed from some increase of rail temperature above the neutral temperature, But now, due to climate changes, we have much higher increase of temperature, and unfortunately, our current tracks are not designed to sustain such a load, and the stiffness of the supporting structure is not sufficient. Now we have a problem in hot days, and we try to solve it. So, in real buckling theory, the potential is buckling is then calculated based on base risk factor, which is a difference between the maximum rail temperature and actual neutral temperature are already defined at the site being analyzed, and some supplemental risk factor which contribute to the decrease of the risk or decrease the risk of buckling. So what are those supplemental factors? Well, the stiffness of the track depends, and also the higher the radius of the curve, the risk of buckling increases. The track grade, the actual operation parameters of the train which runs through that infrastructure, what is the vehicle type, its tonnage, but also presence of hard spots on a track. The hard spots on a track are fields which are used to protect the crossings, level crossings, switches, and so on. And in those points, usually we don't have installed compensation elements which allow the track to deform. But also very important parameters are maintenance activities, history of track buckles, time since license adjustments, and so on. As we see, there are a lot of parameters, and in practice it is very hard to determine all of them and to be actually know all of them. So then we have a problem to actually correctly estimate the risk of buckling. So we try to use a little bit newer approach. We are all aware of predominant use machine learning in all fields of engineering, and we thought we had an idea that these machine learning algorithms can be also used to predict the actual value of rail lateral deformations, and preliminary, because this we will go to some TRL level, we identified several inputs into the artificial neural network model, and these are sleeper type, track curvature, rail track condition, and rail track temperature. And this is where predicted temperatures and the downscale temperatures Alina told you about come into account, as we will use those predicted temperatures to actually predict the lateral displacement of the rail. So, for instance, we made some preliminary experiments in a lab. Of course, we didn't have the full track in a lab, but we use solar radiation, ground temperature, and ray temperature, and we established that there is correlation between parameters, and we can train the network to actually predict what would be the lateral buckling or lateral deformation of the rail. But with every machine learning algorithm, you need sufficient data to actually get the credible results. So to be able to assess all the possible combinations, we came to idea to, in principle, perform measurements and gather data from multiple locations to be able to predict the lateral buckling of the rail in all the possible combinations. So, what are the main possible combinations? For instance, we have rail track curvatures, so we have a straight line curvatures with different radius, and we want to place the sensor and gather the data at different curvatures of the track. Regarding the condition of the track, we can have a new track, track which is recently reconstructed or a quite old track, which quality is not good. But also the position due to sun irradiation is extremely important. So we want to modify or to get the data in different environment effects as for instance, rail track directly exposed to the sun for the whole day, the rail track in a gorge, or the rail track which is partly in a shadow due to forest or some other environmental effects. And we gather some 27 combinations where we will gather data with two measuring stations. Measuring stations in principle measure rail temperature, rail lateral displacement, ground temperature, but also to aid Alina in training of the algorithms she presented to you. For every station, we have a weather station where we gather data about wind speed, wind direction, atmospheric temperature, humidity, pressure, precipitation, solar radiation, luminance, UV radiation, dust concentration, and visibility. And we actually designed those two stations, tested and calibrated them in a lab, and we started to gather data. One of the station is the main station or the master station, and it's gathered the data from the other station as well for itself and sent to our cloud where we receive the data. And to every station you see on the picture on the right side, we have displacement reducers, which are actually measuring the lateral displacement of the rail, and two temperature sensors. One is here. This is the one magnetically attached to the rail where we measure the rail temperature, and the other is put in a ballast stone where we measure the ground temperature. This is a principal schematic of the station where all the communication and power data, those stations are self-sufficient because they are powered by solar panels and can stay for prolonged period of the time. On a rail track, there is a wireless 4G gateway which gathers the data from the both station and then transmits to our cloud. And currently, those stations are on the same line. Alina already showed you pictures of. It's a rail track between Niš and Zaječar. Concretely, this is the part between Niš and Svrljig. This is one of the tracks we will use to gather data. This is a reconstructed track because it was reconstructed some 3 years ago, quite specific because it has a very low radius of curvature. The minimum radius of curvature is 250 meters. And what is also specific, it is passed to a gorge, to a forestry area. There is also area directly exposed to the sun. And overall quality of this track, which is assessed by experts, but not also by experts. We have measuring car data for this track, and for every section we can get a report based on standard where the actual quality of the track is assessed. And what is interesting, Alina already said, there were in 2017 31 buckling on a track. This track last year, even reconstructed, had 10 buckling failures. One of the failure, the biggest failure, was 1.5 meters. The track buckled. and it needed to be repaired. Thanks to infrastructure of Serbian Railways, who is actively participating in this project, we, as already said, all the data, and here we put the measuring station 2 on a hard spot, right before the crossing, where we have wooden floors and no compensation elements, and the measuring station 1 is on a low radius curvature. The curvature of this location is only 250 meters, and there we have concrete sleepers with the data you see on the slide. This is the actuals, for instance, measurements for today. We see that for ground temperature, now it's 20, it was 20 of May. For a ground temperature and air temperature of about 20 degrees. The real temperature was 22 to 25 degrees higher at 4 o'clock in the afternoon. Also, we have historical data for both measuring stations, so in principle, we have sufficient data in this campaign, and we hope to gather sufficient data to actually be able to train the networks. As Alina said, the point is not only to give you the temperatures of the rail track, but also to assess the buckling risk based on the algorithm we develop. Service mockup is shown as an example. You will get a colorful representation, but also numerical, where the buckling risk is below critical. It will be in green, where slightly above or approaching the critical, we will have an orange color. And for instance, where there is a high risk of buckling, a red color will give the network operator a quick overview and prediction what can he expect in the next 24 hours. But not just to develop, idea is to validate, as Alina already told you. We can use Landsat images to validate, but Landsat images are coming at a certain time frame. Idea is to verify predictions of the rail track temperatures with thermally equipped drone. So we will be able to, on the larger sections of the track, actually compare the actual state of rail temperatures and our predicted values. And on the other side, for the rail buckling risk prediction, we want to use the twofold approach because we also have data. We will use data to calculate the buckling risk based on the classical approach. We adopted some of the methodologies which are widely used now in the world to assess the buckling risk with analytical procedure, but also to assess the buckling or lateral displacement of the track by using artificial intelligence. Try to find correlation between the analytical approach and the results given by artificial intelligence, which gives real lateral displacement, and to actually be able to validate with the additional measurements. And because those stations I showed you previously will be during demonstration placed on a section of interest where we will, together with infrastructure of Serbian Railways, assess and see how this can be used in their operational procedures. Thank you for your questions. We will now open discussion, but at the end of presentation, I really want to thank the infrastructure of Serbian Railways for providing great help in installation of the devices, for giving permits, but also for giving credible data we need to develop our system to the expected performance.
Okay, thank you, Milan. Now we have time for questions both for Milan and Alina. So do you have any questions for the presenters? Okay, if you don't have any questions, I have a question. So you mentioned the real temperature measurement that comes from the measuring station. And there are many different criteria to sort predictors by they're important for a specific model we're developing. So what is your opinion, your subjective opinion about measurement, about that measurement, about real temperature as a predictor for the entire estimation of buckling?
In principle, all the approaches, as already said, are using the actual measured temperatures. There are now some new recent advancements, but most of the people are also trying to predict the real temperatures, but based on in situ sensors. So our approach is a little bit different because we use a low number of in situ sensors and use satellite data. But we think that this approach is more efficient than the ones with a lot of in situ stations. And at the end, we both get temperatures which are then used as main input parameter for risk estimation.
Okay, you just answered to my second question that was about Earth observation data usefulness for the entire estimation. So finally, we will have a specific validation and we'll see, but you actually think that the entire new approach that is presented here is effective?
I think yes, because for instance, in UK rail now, because they have a lot of problems because their design temperatures are well below the temperatures they obtain during summer. They using even approach to paint the tracks in white to get to lower the absorption of sun radiation into actual rails. But they are using approach and now they are installing a very big number of measuring stations to be able to get the data for the whole network. But this is extremely investment burden and it's a burden of a lot of data coming from different sources. So I would say it's quite expensive. Using the satellite data, you get an instant overview of the whole network. And it is shown, and we believe that you can get the same quality of the data with much lower investment and after that lower maintenance cost of the operational cost of the whole system.
Yes, you're right. So that was from my side. Is there any other questions? Okay, so if not, thank you once again, both Milan and Alina, for your presentations. And thanks everyone who joined our webinar. So that's it from my side. Have a nice day.
Thank you.
Thank you. Goodbye.
Thank you,
Thank
everyone.
you.
Bye.
Thank you.